over the past 3 years, I have been, like I say, doing a lot of training for UVM classes. And what I found is that a lot of the students make the same mistakes. And a lot of it is just related to misconceptions or not understanding how things work. And so what I thought I'd do is sort of relate some of the things that I have found by showing you some of the common mistakes, common misunderstandings, and things like that, especially if you're just getting started, like some of you probably are. Others of you are probably well-versed, but there's still, I think, some information in here that you might find interesting. If we look at sort of what UVM does, basically it's all about constrained random verification. So the idea is that you enter in random stimulus, right? So you enter in some random stimulus using some of the techniques within UVM to your design under test, and then you get some output. Now, who wants to debug random output? Anybody? Yeah, me neither. Okay. So typically, of course, what you're going to have is you're going to have a checker, C model, some other kind of a system Verilog model, a behavioral level, etc. By the way, I'm doing sort of a quick, get everybody on the same page here. That's why, so again, some of you have seen this before, but don't worry about it. We'll get to some meat here pretty quick. Now, you're running your verification, you're running your stimulus, and you go, when am I done? How do you know when you're done? Well, of course, you got to put coverage in there. You basically put in a bunch of coverage, and now you find out, okay, I've covered most of it, but I've got these holes here that I need to basically fix. So, of course, what do? You add some constraints to target those areas of your stimulus. Okay, so effectively now you've got random stimulus that's actually checking your design, and you can have some reasonable idea that you've got this thing covered. Now, what UVM does is it separates your tests from your test bench, from your verification environment, so that you can reuse the environment over and over again. This is one of the things that, this is one of the reasons why UVM basically allows you to reuse as much code as you can. I mean, this is why the class-based code is used, right? You're using the best software techniques to do your stimulus generation. You don't have to worry about synthesis or anything like that. So, again, the idea is that you try to create a reusable environment, and then you have tests that basically modify that environment, of course, to perform the particular test that you're interested in at that time. We've got this environment then, and what we'll have is our DUT has a number of interfaces that we use to talk to it, whether it's a USB, an I2C, an SPI, whatever it is, right? It's an interface that we're going to be talking to the DUT. And what we use to talk to that is an agent, which is a component within the environment, and the agent itself has a sequencer, a driver, and a monitor. Each of these components has to be built, and so there's a thing called a factory that builds these components. And of course, there's a configuration database that you can use to specify parameters about these different components. So again, I'm reviewing some of the stuff here so that we can actually understand a little bit more about why some of these misconceptions happen. The factory itself is very handy because it allows you to swap in and out. For instance, component classes. It allows you to swap in and out transaction classes. But you have to use it right. And this is one of the areas where I find a lot of the confusion is that a lot of my students don't understand right away how the factory works or what it's supposed to be doing. So we add a couple more agents for our design under test here. And effectively now we've got a reusable verification environment that we can use now to effectively test our design, right? I suppose that most of the designs have registers, right? Anybody registers? Yeah. Okay, everybody's got registers. So what do you do with registers? Do you have to, in your test, basically know exactly where they are, right? Know exactly how they're accessed? No. The idea is that you use the register layer to sort of abstract away that. You describe it one time in one place, and then from then on you use it in your test. Again, and it's all about reuse, right? UVM is all about reuse. And then, of course, we've got things like scoreboards and virtual sequences that run sequences on sequencer. We've seen all this kind of stuff. And then, of course, we have tests that sit on top of this, right? So the test will modify the agent to be, for instance, a different type of agent. So a common one, right, is that you've got a design that you hope will be able to handle error data or data that's in error going into your design. You hope it can actually handle that kind of thing. So how do you do that? Well, you could swap out the transaction class, okay, then generate, parity errors or something like that, right? Or you could maybe swap out your driver. And so the test is the thing that will actually allow you to do those kinds of operations, right? Using effectively the factory to swap out different things. The other thing about UVM that is confusing to a lot of students is that there's a clear definition of when you do things. There's these simulation phases. And so in the build phase, you build things. You build things using the factory. And again, it's clearly defined that it's a top-down process, and that's confusing to some of the students. In this case, we're going to build the environment first. Then we're going to build our agents and subscribers, for instance. And then we're going to build our sequencers, monitors, drivers, etc. All right, then in the connect phase, basically, we do the TLM connections between these devices that allow you to basically pass the transactions around. There's a clearly defined step there. You build first, and then you connect. But the connect is done bottom up, and that's also confusing. Especially the ones that I find that they most get confused about is the build phase. They're trying to basically, they built the top level component, and now they're trying to do stuff with lower level components, and they aren't there yet. So that's a very common one. And we're going to walk through some code examples to show you that. Then there's, of course, the elaboration phase and start of simulation phase, which gives you sort of more control over when you want to do certain operations. These are all about sort of points in time when things happen, right? When things are basically synchronized. So, end of elaboration is a good place to check to see that all your connections are right. Start of simulation is a great place to open files for when you're going to write to output. So we get all this stuff built, we got it all connected, we're ready to rock, right? And so then in the run phase, of course, this is where our transactions go. The idea here now is that this is where all the work really happens, of course. We generate our random stimulus, and we're off and running and effectively run the simulation. Okay, then after that, of course, there's another set of timing points where you can extract things from scoreboards, or maybe check that all your transactions got through. Or there's a number of sort of other kinds of phases that allow you to just make sure that everything is okay. That's sort of how UVM works, right? You build things with the factory. You basically time when you do these things. Let's look at one of the common mistakes that I see with the students starting out, which is the fact that they don't understand, again, how to register things with the factory. The first one we'll look at is sort of the transactions. This macro is what you put in your transaction class, whether it's a sequence item or whatever. And what it does, it basically tells the factory, hey, this bus transaction class, where we basically register this thing so that if I override it later, for instance, that basically it tells the factory that this thing can be overridden. So now what happens if it's missing? Well, then of course the factory knows nothing about the class, for one thing. And see, the problem with these macros from a compiler point of view is they add extra code, which the user didn't type. And so when you get an error, it's in this class over here where you tried to actually build the thing. And so that's the typical error that you get. It's not in this class, in the sequence item class, for instance. It's somewhere over there. And so the students struggle with this one in the component utils because effectively they have no idea where things went wrong. So of course you got to make sure that you include this in your sequence item classes, your transaction classes. The other thing that happens is that there'll be a slight mistyping. Especially I've noticed the folks who are coming from VHDL where case sensitivity just doesn't matter, right? Then effectively, oops, you type the capital B there instead of a lowercase b. Oops, all of a sudden it looks fine. I'm registering. I got the macro, but it doesn't work. These are the kinds of errors that I see and, the things that you kind of have to watch out for. The other thing you'll see is that they'll use the wrong macro. And so, I'm registering this with the factory, but whoops, the wrong macro is used. And so what happens now, of course, is, again, you get one of these errors that says, I can't build this thing because your constructor's got the wrong number of arguments. What does that mean? It means basically that you use the wrong macro, because this components, of course, are expecting two arguments, whereas the transactions are usually expecting one, which is just the name. So these are the kinds of things that really, can be confusing at the beginning. So here's an example of a class where we've actually done it right. We've got serial transaction, we're extending a sequence item, we've got our constructor, and you notice one argument. We've got our data fields, and here's our macro down here, just like it should be. And so effectively this registers the transaction type with the factory. In this case, we're assuming we're going to use a default behavior, which may or may not be what we want to do. And we'll look at that maybe a little bit later. You'll notice also that it has a constraint where it says, hey, we're never going to generate parity errors. Okay, fine, you can do that. We can maybe turn that constraint off later too, right? All right, now for the components, you use a different macro. You use the component utils macro. And again, what this does is effectively registers the class with the factory such that you can override it. And if you don't have this, you're not going to be able to override the class. And the same kind of things happens. What if it's missing? Well, all of a sudden the constructor doesn't work. If you, again, type the wrong class, same deal. It doesn't register the right class. And of course, if you use the object utils macro instead of the component utils macro, now you're back to basically having an issue with the wrong number of arguments being reported. Even though the class has now been registered with the factory, you're still getting the wrong arguments. So again, the way you do this, of course, is you have to have the component. Here we've got a monitor component, which we're overriding, or where we're basically registering with the factory. You can see that we've got the macro, component utils, and we've got a port that we're adding. We've got our virtual interface, right, that we use to talk to the DUT. And our constructor, we build the port. Now again, this is another confusion here, right, where if you add a port, you use new, whereas if you build the component, you use the proxy classes, which we'll see in a second. And that's always a big confusion as well. Again, the constructor for a component needs to look like this, where you've got effectively you're overriding new, because the constructor basically is new, and you call superdot. Again, this is effectively new. New is the base class. I mean, it's a base functionality that you need to call, right, to build something. Of course, it creates the object. Now, the other thing that this does, this superdot.new, it's there basically to add this component, whatever we're building. Let's say we're building a monitor. We're building the monitor from an agent. What the parent link will be pointing to is the agent that's building this monitor. And what the super.new, the base class constructor actually does, follows that link up to the agent and adds this component, again, we're saying we're building a monitor, to the actual children array of that agent, such that when the agent is started, it'll start all its children and start this monitor as well. So again, if this is missing, what happens? Doesn't start up. So, the simulation's running, and effectively this component's doing nothing, because it's basically not there. Now, what if you pass in the wrong parent? We'll see an example of that coming up. But effectively, what happens is that you now don't get the proper reporting happening. In other words, the hierarchy for your reporting is not correct. So it may look like this is, especially if you pass in null or something like this, this component looks like it's at the top of the hierarchy, which is not where it's probably at. You need, of course, a unique instance name being passed to it from a particular scope. And of course, this should be the parent in the component hierarchy that's actually building this component. And if you don't get those right, again, if you pass in the wrong parent, then you can get wrong instance names or names coming up in your reports. The other thing that I've seen is that some of the students don't sort of take care of their instance naming properly. So in general, it's best if this name matches this name. This name is what's used within the system Verilog to point to the particular object, reference, right, to the particular object. And this one is used in the component hierarchy so that the whatever tools that you're using effectively know, well, where is this thing located? Actually, it's again all about reporting. When it actually reports, if you write out for instance, get hierarchical name from wherever this component is, that it knows where it is on the hierarchy. And of course, there's nothing that will prevent you from using the wrong name, but it's much better, of course, if they are the same. So in this case, of course, we've got the instance name and the variable name, system Verilog variable name. Now they're the same. This is much better. Again, nothing's going to prevent you from doing it wrong, but this is, of course, a much better way to do it. The reason why we register all these components with, of course, the factory is that we want to be able to do an override for a particular test. So here I've got the, let's say, the build phase of maybe my environment. So I'm building a serial agent, I'm building an RBus agent, I'm building a subscriber, etc. Of course, because I registered these things with the factory, I can actually use the type ID create here instead of new. And again, what does that buy me? Well, what it buys me is that sometime later, let's say start of simulation phase, after everything's been built, everything's been connected, right? Now I can go in and I can say, hey, I want to override that serial agent to one that generates bad parity. So now I can check that my design can respond or it can react or does the right thing when I send it stuff with bad parity. So again, you need to, of course, have in your serial agents, you need to register with the factory, and then, of course, you can override it by a particular test. Yeah, so start a simulation phase. Okay. Now, what if you didn't use the factory? What if you use new? Yeah, you can build them. You can build your components, and they'll generate these classes only. And the problem is, when you actually go to try to do the override, you're not going to be able to do it. Again, a lot of times what I see is sort of the confusion between using the, why do I have to type all this type ID, create, blah, 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 blah. It's like, and again, it's because you're using the factory, and that's the mechanism for doing that. The other thing, like I was talking earlier, is that a lot of the students don't seem to understand what phasing really is or how phases are used. So, as we talked about, phases basically separate these actions, build, connect, etc., in time. And then it's basically build is top down and connect is bottom up. And that's important because if you're building your top level components, you can't access the lower level ones until the build phase is complete, until you've built everything. And that happens again top down. And if you're in the connect phase, of course, that's bottom up. And then if you're trying to do some connections down low and access some connections up high for some reason, that's not going to work either because we're still down at the low level actually doing these connections. So, for instance, here is a test. And in the build phase, we build the top level test and we immediately try to print the topology. Oops. The only thing you got is the top level. You don't have the lower level components yet, right? Because you haven't built them yet. So that's too early. Again, if you try to access the lower level hierarchy, you're not there yet. So now, if you do something like end of elaboration phase, yeah, everything's been built, everything's been connected. And so now you can go ahead and if you print the topology, yeah, you're going to get the whole hierarchy of your design. All right, so then, as I talked about a little bit already, but let's say that you put null here instead of usually it's this, right? This is the component that's building. In this case, we're calling a type ID create. We're going to try to build a component. And usually what you want to pass here is the reference to the actual top-level component that's building this lower-level component. So if you put in null, it assumes a top-level hierarchy. So now all of a sudden your component's at the top of the hierarchy again, as opposed to being in the actual hierarchy such that when you report your messages and everything, you can see, oh, okay, it's that component that's the problem. Typically, you want to use this. So that's correct. All right, now, scoreboards and other kinds of things, other kinds of components, require a certain number of methods be there. For instance, copy. A lot of times you want to have a copy method because you've got, let's say, a sequencer that's generating your sequence items. And what can happen is that basically randomize the same object over and over again, which is, of course, going to give you good randomization behavior, as opposed to basically randomizing a new object every time, which is going to give you less good randomization behavior. So what you do, instead of, you basically randomize the same object and then you pass a copy. Because what you don't want to have happen is your scoreboard goes in and sort of mucks with the transaction and screws it up for some other part of the design or some other part of the test bench. So you need a copy basically to just copy the data so that, again, because these are all, a lot of the transactions and stuff are references. They're references to objects, which of course, again, if you're mucking around with the references, you can change the wrong data. Secondly, you need a compare, especially if you're doing a scoreboard. It's got to compare the old versus the new, or the expected versus what the actual design is outputting. And then, of course, a convert to string so that it can write out error messages. Basically, that write out what the error was with a particular transaction. And then there's unpack and pack and a bunch of others that are used. So there's two ways to do this, right? One is that you manually create, copy, compare, convert to string, all that stuff yourself in your transaction classes. The other way to do it is using field macros. How you do it, I think, depends on how sophisticated user you are and whether or not you actually understand field macros. Now, the thing about the way that these manual work is that you'll say something like copy transaction2.copy transaction1 in your code. And so now it should copy all of the data from transaction 1 into transaction 2. And now you can use transaction 2 wherever you want, and you're not going to muck with transaction 1. But what's interesting, of course, is that it calls the do copy. And this, again, confuses the students to no end. Because why isn't it just copy? That's one area of confusion. Of course, the other one is the compare. It calls do compare. And so the point is, you basically have to override these methods, do copy, do compare, and convert to string, for your particular transaction class. If you're going to use them with, for instance, a scoreboard or something like that. You can, of course, do this manually. And let's say that you do actually override the compare method. Then, of course, what you have to do is you have to turn off the compare for the built-in compare. Otherwise, you're going to get the anding of the results, right? In some respects, it's almost easier just to use the field macros to begin with, although, again, you have to know what you're doing. So in this case, we're using all the default copy, compare, etc. for this particular field, the built-in ones. And we're going to display this one as hex. And we're not going to compare. We're not going to call the built-in compare method, or the default compare method. And again, because we are actually doing it manually ourselves. It may be because, for instance, there's a field that you don't want to compare, or you don't care. Maybe it's a data field, maybe it's some other field that you just don't care. Now, of course, to do this using field macros, it's easy as long as the fields themselves lend themselves well to the field macro field specifiers. Things like int, arrays of ints, enumerated types, and things like that. There's, of course, a lot of field specifiers with those. And then, of course, you can just use UVM default for how do you copy, how do you compare, because you've specified what the type of this thing is. So now it's pretty straightforward for how it's all compared, etc. All right, so that basically, capabilities and the radix for how these things are done. Another confusion, I've actually had this bite me once, is the fact that in the past, super.build phase was used in a lot of examples and things I played with. And what you don't realize initially when you first get started is that it actually calls a function called apply config settings, which effectively takes any config DB items that are meant for this particular component and applies them to the component. And so if you have, so if you call super.build phase in your build phase, right? And all of a sudden some of these items that may be set in the config DB show up and change some of your initial values. And that can be surprising and kind of difficult to understand what happened. So for instance, now this is probably not a smart way to do this particular set, but you'll see the idea is that, let's say I have a config DB set where I'm specifying count to be the value 1000. But what I've done is I've said, okay, starting from the test and apply it to anywhere. Yeah, probably not a good idea, but for this example, we're showing how you might do this. I mean, it could be that it's a global thing, and that's fine. But just pointing out that in general, you probably want to target these things more directly. Okay, so we've got count set in our config DB, and now count is going to actually be applied to this component because we called super.build phase, for instance. And now We've got a local value count here. And yeah, we call super.build phase, and all of a sudden count gets set to 1,000. Whoa, what happened? Anyway, it's one of those things where if you don't do it carefully, it can surprise you. The other thing that I have seen is that some of the students really don't get the idea with behind the TLM ports. And even the folks, well, they'll basically implement connections or data transfers between components using events, which is fine, you can do that. But the problem is that you have to debug that. Whereas if you use the built-in TLM port, it's a mechanism that works as long as you know what to do, as long as you know how to do this, it basically works out of the box. So, for instance, in my monitor, I've got my analysis port, right? In my, let's say I've got an instruction set simulated that's representing the next transaction or the expected transaction that's going to be coming out of my design. Okay, so I've got an export on there, and then by the fact that this is an implementation, I need to provide a write method here, okay, such that the monitor, when it does its port.write, it basically passes the transaction over here. And then all you need to do is just connect these two up, right? Connect the analysis port to the bus monitor export in my environment. Again, I've seen a lot of the students basically not understand, number one, that when you have an implementation, number one, you have to specify the fact that the classes have to be the same. And number two, that you actually have to provide a write method there. But if you understand these kinds of things, then again, it's a built-in, tested, proven kind of thing that actually works very well. As I said, I've seen some students are trying to do like creating events and passing the data with events, and it just makes it more work. The other one that really drives them crazy is config.db. In this case, let's say in our config.db, we've got a set of some UVM bitstream type. So we're actually trying to set whether this agent is passive or active. The thing that really confuses them is the fact that there are 4 arguments to the set and the get, and they have to match up. Oh, and of course, the types have to match. First thing, of course, is that this type matches this type, and they have to match exactly, right? Secondly, where's the hierarchy starting? Now, in a lot of cases, I've seen that the set is done from, let's say, null, from the very top. And then the next part, the relative path, is going to target to a specific component within the verification environment. And then I've seen where the get down here, effectively, they just call this, and then nothing for the relative path. But the point is that these two have to match up, right? The path that you set this value to and the path where you get the value from have to be the same, or they have to match up. And of course, again, the type. Then the name of the field itself has to match exactly. And I've seen lots of errors here again, especially with case sensitivity and those kinds of things where all of a sudden, I said it, but it's not being gotten. Well, you misspelled it. And then, of course, this is the value you're setting, and this is the variable that you're trying to assign. So that's the other confusion, is the fact that this is where you want to put it. Effectively, the type, the hierarchy, starting point, the relative path, and all this stuff has to be all, the stars have to align basically for this to happen. Now, the other thing that confuses students is the fact that what if you set a config.db, a set variable value, in multiple places in your hierarchy? Which one wins? So let's say I've got a driver down here. Basically, its path name is effectively A, B, D, and F, right? A.B.D.F. So down here, I'm going to search for something called name. All right, well, if I go up here, I can see that star.D.F, name equals value. So this is the path name, and sure enough, star.D.F matches my driver. And sure enough, I'll get value 3. Okay, so far so good. Now I can see, oh, there's another set here. And again, this basically, this process happens during the build phase. Here now it's got A.B.D.F. Okay, name equals value 2. Okay, so that also matches. It's higher in the hierarchy. So now this one's the winner. And then finally, I've got well, first of all, PQR, don't care. Doesn't match me. But A dot star does match. And so I can see name equals value 1. So effectively, this is, again, higher up in the hierarchy. It's at the test. And so this is the winner. What Srivatsa is going to be talking about next is some of the ways that you can actually look at, well, what have I set and what have I got? So I'm trying to talk more compile time. He's going to talk more about sort of runtime ways of actually debugging this kind of stuff. The other one that really causes lots of confusion is in a sequence, this UVM do. So first of all, a sequence has this rec item automatically defined. I mean, it's in the base class. And so the students look at the code and they see some repeat loop with a UVM do in it. It's like, where the heck is this rec thing coming from? And again, it's defined in the base class. And of course, they have no clue what the UVM do really is doing, which is, of course, these 4 lines here, which maybe it's better to actually use, instead of using the macro, which you don't understand, maybe let's do this. Anyway, so what it's doing, it creates the object, it does a start item, tells the driver, for instance, hey, I got an item for you. And then once the driver comes back and says, hey, get, basically, I need an item, then of course this sequence randomizes it, and then finally, here you go, off you go. Again, what I see with a lot of students is they do not understand what exactly is going on here to begin with, and of course, the fact that this thing effectively comes for free. In fact, there's a whole bunch of macros that effectively provide a lot of this capability. For instance, there's a create, there's the do, of course, then there's do with priority and with some constraints associated with that, so inline constraints. There's the send and the send with priority, etc. There's a whole bunch of these macros, and what I've seen, for instance, sometimes is that somebody will do like a UVM create, maybe then a UVM do. It's like, well, you already created it. You don't need to do the create again. Or, for instance, a UVM do and then maybe a UVM send. It's like, well, UVM do sends it already. So there's a lot of confusion around these macros especially. And so I just tell them, do this. Do the 4 lines and you're done. For instance, here's an example of, you can, of course, UVM do with some constraint, right? UVM create, send with some constraint. Here you can do a create, then a randomize, and then a send. And all of these are equivalent. They're all just using different macros. The other thing that gets a lot of confusion is the fact that if you look at your timing with respect to the driver, the sequencer, and the sequence that's running on the sequencer, really the driver is the only one that should be concerned with the timing of the DUT. The DUT itself, the driver is the one that has the pin level interface here. The driver effectively can see, okay, there's a ready signal, there's a whatever it is, that the driver is the thing that has the pin level timing. And basically between the sequencer and driver here, this should be purely a TLM connection. And it should be purely procedural. And the way that the sequence talks to the sequencer basically generates a new item, right? So if we effectively, the driver says, hey, I need a new transaction item. The DUT's ready for me to send some more stimulus. I need a new item. The sequencer, okay, great, going to go generate some new sequence item when asked. And of course, the sequence itself is going to generate that based on, of course, the constraints that are used to do that. Now, here's what you don't necessarily want to do. I've got a sequence, right? Here's my body task, which of course you need to have because that's what actually is run. And so I've got my repeat UVM do, okay, using the macros. But you'll notice that in here I've got some event that it's waiting for some event from the DUT. Yeah, that's probably not what you want to do. Again, this kind of timing should be down in the driver such that the driver, which has, again, all of the sort of the pin level activity, it knows what the DUT is doing, is ready, effectively put those kinds of things. So here's the driver now, and of course it gets the transaction. And now it can actually, this actually makes much more sense. Again, it may not be an event, it may be, for instance, some signals that it's looking at to say, okay, the ready signal's high or whatever. But the point is that the DUT timing belongs in the driver as opposed to in the sequence itself. Another confusing thing is that, again, the driver and the DUT talk through interfaces, right? So you'll use basically an interface which specifies what are all the signals that go between the driver and the DUT. And in a lot of cases, you use mod ports. So there's maybe a mod port for monitor here, that this is the one that this monitor component of a particular agent is using. Now, is that mod port required? No, it's not required. It adds checking, but it's not really required. And so, in fact, here we got a mod port for the DUT fabric. Here we got a mod port for the test bench monitor. But, yeah, it adds checking, but it's not really required. That's the point. So you can send the entire interface here, and whether or not you actually use the mod port in the monitor or not is really kind of up to you. A big one is objections. So objections have to be managed properly. Now, an easy thing to do, of course, is to put them around your stimulus. And that's the most common thing that I've seen. And that works well. But there's always the issue of that last transaction. So the stimulus is completed, the sequence is done, the last transaction is going through your test bench. Maybe it gets through into the bus monitor, and it's making its way through, let's say, the instruction set simulator. It hasn't gotten to the scoreboard yet. And the simulation stops because you've dropped all the objections. So what's sort of the best way to get around that? I mean, obviously, like I said, raise up an objection before so this is the stimulus. We're running some sequence on some sequencer. Yeah, no worries. And so we basically raise an objection before the sequence starts. Sure. And then we drop the objection after the sequence is completed. And that, again, that's probably most of your objections that you need to do is effectively around the stimulus that's being generated. But as I said, there's still that one transaction that may be making its way through the rest of the components, and it hasn't got there yet, and then the simulation stops. And so now it may not be a big deal, but again, you could be expecting that transaction to do a specific thing within the scoreboard, whatever it is, and all of a sudden now you don't get it. So one thing you can do, which works pretty well, is you can actually set a drain time. So what this is going to do, after all of the objections have been dropped, the simulator will run 100 nanoseconds more, which may be good enough, but it's not in general reusable, right? Because you don't know how long it's going to take for the simulation to actually deal with that last transaction, for instance, and then get through the rest of the design. So that works, I think, for most cases, and especially if you know the design well enough to understand how long it's going to take for transactions. Does this guarantee that they run all the way through? It doesn't, right? Because you could still have an issue where a transaction doesn't make it all the way through. So the other thing you could do is in the actual, for instance, driver or monitor or whatever is accepting those transactions, you could say, hey, get my next transaction. Okay, now I raise an objection in the driver itself, which is at the sort of the bottom of the tree, right? And now we're not going to stop the simulation until the driver's actually done with the transaction. Could be good enough. But the problem is now that if you're raising and dropping these objections sort of per item, and you've got millions of items, this can actually become quite a simulation overhead. So I would say, yes, you can do this, but you're going to have to, of course, do this judiciously so that you effectively don't cause too much simulation overhead. And the other thing is that the objection itself will propagate. So down here in this driver, we basically propagate the objections all the way to the top, which again causes a lot of simulation overhead. So what you can do is you can turn off propagation, so the objections remain down here. So you do something like this, where you say, set the propagate mode to 0, and now the objections basically don't propagate up through. It saves you a lot of simulation time, maybe. And so it should minimize the simulation overhead, right? I've basically given you some of the things I've seen with the students, confusions, a lot of the confusions around, I would say that the most confusions are around the factory, especially like the macros and things like that. I would say that the config DB is a close second. And beyond that, objections. I'm forever seeing students that get all their stuff sort of built right? Fire up the simulation, and it stops immediately with nothing and not understanding what happened. And it's because it didn't raise any objections. I would say that some of these things can be pretty subtle, and especially when you get no error messages. As I said, the system Verilog compiler expects you to know what you're doing. And so it really won't give you a lot of error messages if you are doing things that are, like some of these subtle kinds of things. I would say follow the tips to make sure that you do the appropriate, add your macros and check your config DB. And again, Srivatsa is going to talk a little bit about how do you actually check some of this stuff. Now, the other thing you can do is that on the Doulos website, there is this easier link here that's really useful. There's a UVM creator. You basically fill out a template for what your design needs in terms of components, etc. And it creates effectively the base shell, if you want to call it, or it creates the code, pretty much all the code you need except for the BFMs for your particular test bench. And from there, fill in your BFMs and start building your tests. So it's a very handy tool to sort of jumpstart you and get you going. So I would definitely check that out.
My name is Srivatsa Vasudevan. What we are going to do is to cover the runtime issues that a lot of people face during a UVM simulation. There are a few common tips and tricks that are being presented through these slides. So the first thing I want to cover is to go over the factory issues. In order to begin, we look at a typical UVM test bench hierarchy, wherein you have the test called as UVM desktop, which instantiates an environment, which instantiates an agent. The agent itself has a driver sequencer monitor hooked up to it. Now, looking at this, after the environment is completely constructed and the test is running, there is a scenario where a number of transactions are actually fed in through a driver of type SP transaction that are now fed into a command component. The command component is under construction. After the component has finished observing it, the monitor actually is observing what is happening, and the results are then fed to a scoreboard. So that's the S2P transaction that is created, goes into the component. Now let's assume that you are now trying to create a new type of transaction wherein there is a slightly different payload pattern. This may be that the transaction itself has a few additional constraints, or maybe there are some other variations to the data wherein you have corrupted the CRC or any one of those kinds of applications. When you had to now do this, you now have to replace the original S2P transaction with a new type called S2P transaction with payload pattern. How is this accomplished? This can be done using the factory that was introduced in the previous section. You can do some overrides at runtime rather than at compile time, and you can do this somewhere in the middle of the test. So during simulation, when the test for the factory is actually run, during the build, you may have chosen to replace it right at the beginning. So this new S2P transaction with pattern is overriding every instance of S2P transaction throughout the simulation. And in the driver, for this example, when you use the factory, you will notice that although the S2P driver was supposed to be using S2P transaction, it now uses S2P transaction with pattern. It's actually truncated here. And that is actually shown when you do a print. Life gets very interesting here. One of the key debug suggestions that is offered is to actually do a couple of prints during the build phase so that you can actually see what is registered with the factory and what objects are there. We'll go over that in a minute. So in this animation, you'll see that this message is actually coming from factory, and then you see this at runtime. Let's go over some overrides. The overrides that are described here are of the type where, in the previous example, we were talking about S2P transaction now being replaced by S2P error transaction, wherein you are looking to inject some errors into the duct. So you can set type override by type, which basically does replace all the original type, which is S2P transaction, with S2P error transaction. And After issuing this command, at some time later, let's say that you choose to replace with the original S2P transaction with S2P new error transaction. Then you can put in an optional replace argument. By default, this is the first override. A little while later, when you choose to do the second override, remember that the default replace is 1. So the factory now will create new objects of type S2P new error transaction instead of S2P transaction. And this is the default. This is the default behavior of the factory. When you do this replacement, what happens is there is a message printed with the ID TP-regger that you should be looking for in your log file. When you see this message, you will also see that the original object type S2P transaction was already registered to produce S2P error transaction. I'll go back so that you can see. It looks a little bit subtle. The original override had S2P transaction. It was overridden to produce S2P error transaction. And sometime later, you took S2P transaction and then tried to replace it with S2P new error transaction. And that's the message that you see. You will see this message. You don't see this message, something's gone wrong. There are a couple cases when it does not happen, and I'll cover that in a minute. Now, let's go back to the same example. The S2P transaction is now overridden by S2P error transaction, and then sometime later when you did it, you're going to have S2P new error transaction, but you set the dot replace to 0. When you set the dot replace to 0, something rather interesting happens. The new objects that are requested from the factory belong to the original type, which is S2P error transaction, not this. So you will get a message. It's slightly different this time. The message will say S2P transaction is already registered to produce S2P error transaction. If you have not set the replace argument, just remember that replace by default is 1. The factory will replace by default, but you can choose to override it. When you override it, what will happen is that if you have not set this replace argument, the factory will continue to produce objects of type S2P error transaction. Is it possible to replace them in instance-specific overrides? Unfortunately, there is no feature in the BCL for instance-specific APIs. You will only find it in the type APIs. There's also no warning from the library in case you're trying to do it on instance-specific overrides. I want to now talk a little bit about factory debug. Sometimes you wonder, why me? That's happened to me a lot, especially when you have 2 or 3 types of objects and you're thinking, hey, look, I was expecting this new type, but I got this other one instead. Why me? Because it's somewhere in the middle of a simulation that's probably anywhere between 4 and 6 hours long, and you begin to wonder. So these tips and tricks are fairly common. We bring them out here to explain how to debug. The factory has a print method, and this print method has a number of options. The options, we'll go over the options in a minute, but what you will notice is that although this is not a static method, you can put this in at the end of the elaboration phase, or pretty much anywhere you want to call it. It actually works. So what is not shown here, this is a 1.1 type of thing, but the 1.2 thing is very, very similar. What you do is get a handle to the factory, and then you can do a factory.print. There is an optional argument called all types, which I'll cover in a minute. And what that all types argument does is to control the output that you see. And depending on where you are and what you're doing, you may find that output actually fairly useful. Srini recommends using all types 0 and instead of the default, and we will go to that in a minute. Let's look at the default. If you were to print from the factory, what you will see is you will see this output wherein it tells you the requested type, the override path, and the override type. It also tells you no type overrides are registered at the factory, and it gives you a list of types that are registered with the factory. So you get this list. And remember, this is where things can get interesting. if you have an SOC model with maybe 10,000 registers, all of them registered with the factory, that bottom thing is going to contain 10,000 lines. It can get very long. Okay, and if you're printing this multiple times in a simulation and you're trying to find that one little override, you're going to be digging through a lot of text, either doing some Perl or regular expression matching. There's slightly a better way. Look at this. When you say all types is equal to 0, you will only get the information about what are the overrides that are processed by the factory. The rest of the types that the factory knows are suppressed. It's a neat trick because then rather than looking through screens and screens of data, you can effectively just say, hey, look, did my override type or instance override get registered? Does the factory know about it? What exactly is going on? There's a third argument, and this can be useful only in some situations, is that when you set all types equal to 2, all types equal to 2 is not the default, all types equal to 1 is, but you will get a listing of all the UVM classes as well. And depending on your simulation, it can be pretty big. Might want to use this option with some level of care, especially if you're going to do some overriding of the existing classes or you're doing some fairly interesting work. This may be something to consider. But in general, we would recommend looking at either all types equal to 1, which is the default, or all types equal to 0. If you have to do some fancy debug, then go ahead and use all types equal to 2. This is documented. You can pick it up from the documentation of the library and just change the output and you will see the difference between all the three. And that's the reason why Srini has this for your eyes only. Looks like he really likes the Roger Moore rather than the Timothy Dalton. So how many of you have put in an override and you're saying, gosh, I wish I could override it back. I want to go back to what I had. That is, I injected 10 or 15 error transactions and I now want to go back to my original type because it was way too much work to create a new transaction. So this is where a new feature in 1.2 called undo can come into effect. It's actually fairly useful. It's not present in 1.1d, and I go over that. So let's go back to our original example. We've got S2P transaction and S2P error transaction. And then you can go back sometime later and then put back in the same type as the override type. This is new in 1.2. In 1.1, this will give you an error. You will get a duplicate type error message. You will not get this error message in 1.2, but you will get this message in 1.1d. This is a new feature of 1.2. So in case you see a difference between 1.1d and 1.2, especially if you have mixed level environments, this may be something to take care, especially if you're using 1.2 features and suddenly you migrate down because other environments are going to work only in 1.1. So just watch out for this a little bit. But if all your environments are 1.2, this will work quite well. I'm going to go a little bit over the naming that happens during the factory. Here is something that Doug already covered about the names that are used when you create components. The example on the slide here is how to use the name string itself in order to determine, during the overrides what exactly happens. And I'm going to cover some examples of what happens when you do that. So there's two parts to this. There's a name and a component, and the name is now default. It's a mandatory part in the constructor. So let's look at what happens during the build phase. So the S2P driver here uses the create method to create the driver. And this string here that is passed to it is called S2P driver 0. The sequencer has S2P sequencer 0. That's the name that's passed during the create. And this name is fairly important. One of the recommendations is to keep it the same as the name of the instance so that it's easy to debug. But you're allowed to put any name that you like. It's a string. It could be your credit card number, right? But then it has some fairly interesting implications. And that's why Srini has this photo of a baby which is loudly protesting its name, saying, "You're going to call me what?" So let's look at what happens when you give this name and what are the effects of choosing a slightly different name. There's two snippets of code here. There's one snippet of code here. That's the top-level test case that instantiates an environment. And the bottom is the build phase. And we'll go over that one by one. The top-level test case has an instance of the environment called AXI Fabric env0. And then during the build phase for the test, he calls super.build, and then he creates the AXI Fabric environment using the factory pattern, but he gives it a different name called crazy env. Notice that this name is something new. It doesn't look like what you're normally used to. So this AXI Fabric env0 now has a name, crazy env. So what is it that you expect? Let's go look at what happens during the overrides. During the build phase, when you try to set an override by type, if you look back, you will see AXI Fabric env0, which was the instance name that you were expecting. However, you will notice that it will fail because you named it something different. You were expecting this to be a part of the hierarchy, the elaborated hierarchy, but that is not the case. In the second example that is presented here, you're using a star, which is fundamentally a wildcard. It will match everything. It will eventually find this guy because it's a wildcard. It's a wildcard match. So you get something, but if you have two instances of the environment, it will set it in both. If you're trying to constrain only one, you now need to give that name. That is the reason why this name is so important. What you gave in the previous stage is going to matter a lot. This is the best of the lot, wherein you're constrained it to only the agents that are inside AXI env. In the previous case, if there were 2 or 3 instances of the AXI env, it would be set in all of them, and the top one would fail. Again, you will see that there's a debug message here of all type 0, which would have pointed out that the first one did not work. If you had commented out these two, this debug message would have basically told you, hey, look, I don't see nothing. The second and the third would actually show you a message. We've covered the factory so far, and we've gone over how various overrides are possible with the factory. We've also covered how the naming controls various aspects of this thing. We're now trying to move to a different phase, which is objections. So no news is good news is fairly popular, but what I'd like to say is if nobody objects, the test is basically going to end. What happens is that UVM uses an objection mechanism to determine whether a phase is ready to end or not. If there are no objections to a phase, as Doug earlier mentioned, nobody's waiting, might as well go to the next phase. And this is where some things get rather interesting. Let's take a look at the example that we've got here. You will notice that he has an example where he sees the driver where the reset is running. It seems to be running. He sees the sequence is now started after reset. And then suddenly, at 100, boom, the test is gone. Hey, look, my design went through reset. How come the sequence didn't run? And that's because during the main phase, there were no objections, and the test terminated early. There's a blog article about this in quite some detail, but we'll go over the objections in a second. So one of the recommendations is to raise an objection, as Doug had also explained in the previous phases. This is very, very important. If there are no outstanding objections to a phase, all threads that are forked off during that phase are killed, and the phase comes to an end. So when you start your test, you raise an objection, you run the sequence. After the sequence is done, you wait for the sequence to finish, then you drop the objection. Now you might wonder, how do you debug this? Okay, there are a couple of tricks to debugging this. One of the ways to debug this is to use the phase tracing. The phase tracing is built into UVM. What you can do is turn on a switch And when you turn on the switch, what will happen is that you will get a bunch of messages in your log file regarding the phases themselves. All the common phases, a lot of information is actually printed in the log file, and you can just go through the messages either by gripping through them. And what you will notice is there are no objections for certain phases, and that is why it is skipping the phase. So there is a recommendation here on how to figure out who is objecting and who is not objecting to a phase. What's done is that you have a separate task that's sitting inside a forever loop. And during the phase itself, you can just do a display objections. And what that does is that it prints out, it's built into the UVM library, and what it does is it prints out, as you will see on the next slide, a list of all the people who are objecting to the end of the phase. In this example, you will see that when that function is called, you will see that the total objection count was 3. And who are the people who are objecting to the phase ending? So you know exactly where and who are objecting to this phase ending, and you can keep going till you hit to the hang state. So the trick is to just leave it in a forever loop when you're trying to debug, and then just keep displaying the objections till you hit the hang. And once you're done with it, please remove that piece of code. Fairly advanced topic here, phase jumping. UVM does allow phase jumps within the same domain. If you actually have a long setup, there are some recommendations from Srini on doing phase forward and backward jumping. And he has a couple of examples in here about jumping between the various phases. Doug here had gone over the various phases, the build phase, the connect, the lab, and other phases. I assume that you're familiar with all the phases. Now that you're in the run stage of the simulation, sometimes you may find that your setup to actually get the device into a state wherein it's actually in a position to accept transactions may be quite long, maybe several hours. So phase jumping is one technique which has to be used with extreme care before you do it. And I'll go into some of the caveats much later. So let's assume that you're trying to go through reset, configuration, main, and then shutdown. Configuration, main, shutdown. If you're trying to do something of this sort, or go through reset and main. There is a callback called phase ready to end callback, and you can add that to your top level test. And we'll give you some example here of how to use that callback to implement a phase jump. This is a setup slide. This setup slide basically goes into the detail of the various tasks that are there in this subsystem. There's an example of cricket innings here, wherein you're trying to take a break, wherein you've gone through the entire process once. And at the time when you're ready to end the main phase, what is implemented here in this piece of code shows you how to actually try to loop back. In this example, what he's done is to check for whether it's in the post-shutdown phase. And if it is indeed the end of the post-shutdown phase, he just checks a variable called number of jumps. And if the number of jumps is more than 0, he's expecting this to be a counter that tells him how many times to go through the main phase. What he's done is he prints out a message that says, I'm jumping back to the end of the pre-reset phase. And then he does a phase jump. And then he gives it a phase argument that says, please go back to the pre-reset phase. And then he decrements the number of jumps. If number of jumps was 0, he basically ends the test. This was on the first iteration. On the second iteration, life gets a little more interesting. At the ready to end, now number of jumps now drops down. Let's say there was 1. So it goes from 1 to 0. And he's decremented it. And then the second time through the loop, number of jumps is decremented. So since it's 0, it basically gets out here. There are some caveats to this, in the sense that you have to be a little careful when you do this. When you end the end of a phase, all tasks that are during that phase are killed. So if you have any sequences or anything that has been running during that phase, just remember that when you do the jump and you go back up, those objects may not exist. The garbage collector might have taken them, cleaned them out, done things with them. And you have to be a little careful when using this methodology. But what happens is that you can basically skip through a lot of the initial setup that may be required. Also remember that your VIP or any other IP in the simulation, I'll cover that in a second, needs to go through this. And that is what this slide is describing here. See, by default, what happens is that when you are in a certain phase, all the components need to finish that phase before you're allowed a jump out of the phase. You cannot have a VIP1 in main and VIP2 in reset. All of them will be in the same phase, which also means that you have to make sure that each of these VIPs is capable of handling your jump. I want to go a little bit over a concept of UVM domains. UVM domains are collections of components that must advance phases in unison. The key thing to remember here is that between two domains, the exact phases need not be identical. So you have the UVM library set of phases, and you can have your own domain. You can create your own domain. There's a couple of papers by Doulos that talk about adding domains. They're nice papers. And what happens is you can have VIP 1 and 2 in domain A and VIP 3 in domain B. And when you look at this, you will see that VIP 3 may go through this sort of a sequence, whereas VIP 1 and 2 may go through a slightly different sequence. And they're in different domains. And you can synchronize the beginning and end of the domains. And then additional domain, you can choose to add additional phases or pretty much do anything you like. As long as you set it up in the schedule properly, it would work well. There are some guidelines to phasing that Srini puts out. To use the correct phasing, use objections. We're going to talk about the command line processor in a minute for debug. We just talked about how to display the objections. And he believes jumps are cool and useful. Some of us may agree, some of us don't. And you can also use domains. He wants you to call him. I'm going to go back to the config DB to touch a little bit more on what Doug had covered in the earlier presentation. Typically, field name and the value are usually kept the same. You can change them. It can be anything you like. There are some gotchas when you use the config DB, but not a must, but set and get must at least agree on the field name. And I'll go over that in a second and how to debug when something goes horribly wrong. Let's look at this. So you got field name versus value. So what happens is during the build phase, all components attempt to get some values from the config DB. You'll find a field name was active and the actual value is the is active, if you recall from Doug's presentation earlier. And then you can have a warning for the is active bit. Usually a good idea to print at some level of verbosity what you got, so that you don't have to recompile. This goes a little bit now into the set, wherein you've actually set the dot was active. This would be a recommended practice. As Doug had mentioned earlier, all the context, the instance name, the field name have to match. To some extent, you can have some control over the thing by using this coding style. Here, in this example, he has wildcards, and he sets a context of this, so which means this and below. What happens now if this doesn't match? Let's go over that. This is a big problem. Okay, you run, it's very hard to detect what happened. There are some handy debug functions. Some of them you already know, and some of them we'll cover. There is a function called check config usage that is built into the component. Okay, it's there. You can use it. What you can do is just at the start of simulation, you can just call this method. When you do that, what happens is that you get this rather interesting message that says the following resources have at least one write but no reads, which basically means in English, somebody wrote to the config DB and nobody got it from the config DB, or in other words, something didn't match up. All you have to do is call this function, it'll spit this out. It will also tell you, in this example, that nummasters set had a value of 3. That's on the slide. Nummasters had a value of 3. You did a set. One write happened, but no get happened for that variable. That comes from the check config usage thing. It can be very handy. All you have to do is to put it in at the start of simulation, because by that time, as Doug had explained earlier, all the components are built, hierarchy is built, whatever configuration you have applied is ready to go. Now that you have done this, sometimes you want to get a continuous output of everything that's in the sim, and that's what the next slide here covers. During the main phase itself, assuming you have done a set, you can also do a print config. It has a couple of arguments. A recurse, which basically says, please walk through every level of the hierarchy, and you can turn on an auditing bit. And I'll cover what the auditing bit does in a minute. This is actually a fairly interesting feature that's built into UVM. And this is the sample log from the audit. It looks similar to what we saw earlier, but it has pretty much everything. Here you will see again, it tells you number of masters, number of jumps, the jumps from the previous example that you saw. And then you can see who read what, who wrote what. It's a fairly cool feature. All you need to do is to turn on the audit. How many of you are dealing with very long simulations? Well, there's quite a few of you. Yeah, don't you hate it when you have to recompile something to find something out? You really do, right? You begin to wonder, why me? So there are some options from the command line processor that might be able to help you. And that's what I want to cover in the next section. What happens is that after the executable has been compiled, as in the case of compiled simulators, you don't actually need to go in and add a few more statements, recompile. You might be able to get some information from your existing compile. And especially if your compile is several hours long, you just saved yourself several hours. And that's what I'm going to cover over in the command line processor. Let's say that you had 10 errors in the sim, and the simulation actually took 6 hours. But the first error happened maybe after an hour, and the second error happened 30 minutes later. So about an hour and a half into the sim, you hit 2 errors, you were done. No additional information was going to be got from the sim. Since everything is reported with the report error or using the tick UVM error macros, there is a hook into the reporting system from the command line processor. What you can do is pass this additional command line to your simulation. The processor will pick that up, and it will quit the sim after this number. Here it says 2, but you can give technically any number. The default is no limit. There's basically no limit. It's only aware of UVM error. So if you have SVA blocks or DPI calls, you need to go back and instrument those to use UVM error in case there is an error in any of your blocks. Because then it will use the UVM error infrastructure in order to leverage this capability. The trick here is, again, to just put plus UVM max quit count equal to some number, and it'll stop as soon as that part is done. Anywhere right in the middle. There's a few additional command line options for debug. A couple of them we have covered, and a couple of them we will go over here. The UVM phase trace is something that turns on tracing of phase execution. What this does is it prints out a message every time you are in one of the phases, telling you that a phase is about to begin or end. And you can use that to figure out if something is hanging somewhere. When you combine this phase trace with UVM objection trace, you can see who is objecting to the end of phase. In case you have a hanging simulation, the combination of the first two actually will tell you, look, one of the components is misbehaving, or I did not get back a response to something or the other. So you can get some fairly detailed diagnostics between the two. The objection trace actually prints out a fair amount of output, and the phase trace will print out some. So be prepared to post-process a little bit, especially if you have a large sim. The resource DB trace and the config DB trace are basically stuff that turn on the set and the get. And these two also will help you to actually figure out where your configuration has gone. So let's look at a config DB trace. I assume most of you are familiar with this, but here goes. So basically what happens is that there is a configuration set for a certain variable at the top, and then for this corresponding thing, you will see a corresponding get. The set and the get, as Doug had explained before, have to match. If you do a get for something that doesn't exist, you're going to get back a null. And depending on what's happening in your sim, it might actually do something or not, depending on if you had defaults. So the set and the get have to match. And as Doug had explained before, the context, the instance name, the field name have to match. And the types also have to match. And that is what this thing will explain. The next slide actually shows you how many counts you got. You will see you had 141 gets and only 2 sets. This count can be actually fairly useful to you. UVM objection trace actually goes in and gives you a trace of every objection that is added to the global count. And what you can do is see who had added an objection to the phase ending, who had added one, and who had deleted one. So in case you have an additional objection that got dropped, the counter will go to 0. That is something that you can find in this trace. For example, you accidentally put 2 phase drop objections in a piece of code. It will show up here. The ID for this one is the objection TRC, which you will see. Let's go over some popular options. UVM test name is equal to my test. We'll basically execute the test that's called my test from the factory. It will override the value that's in the code. This is a common command line option. Here's the gotcha. It will only pick up the first one. If you have multiple UVM test names, it will ignore the second. And you might wonder, hey, look, I should have run one and then run the second. It doesn't do that. It will only pick up the first one. This is something to watch for in your scripts. You will get a warning, but you will wonder why your second test didn't run. The verbosity setting. Here's an example of setting a verbosity. What happens is that you can set the verbosity for a certain component, for a certain ID, at a certain verbosity, in a certain phase, or for a certain time. It gives you a fair degree of flexibility. At a certain time, you may suddenly decide that I only want the verbosity to be at maybe 800 nanoseconds into the sim through about 1200 nanoseconds, and I don't care about anything else. You may choose to say, I do not care what the verbosity is at other times. Rather than adding a piece of code to the simulation, you can just do this from the command line. There's an example of this here. And one thing I want to highlight here is that once you set the verbosity, there is a special keyword called _all_. That sets it for everything, all the IDs. It sets it to full for time starting at 800. You can give 800, 900. So you can just turn on the verbosity for a certain portion of the sim, look at it, and determine what's going wrong. Especially if you have a couple of print statements that are put in there at a higher verbosity, you can only turn it on for a certain one. That way you've saved yourself at least one recompile. You can choose to upgrade something to an error for a certain component. You can do that also from the command line. So you got the original severity, replace it with the new severity. It will do that for that particular component for that particular ID. Here's an example of that. What you can do is you can change UVM info to UVM warning for the scoreboard if you're looking at some scoreboard issues. You can change the effective action on messaging also, and that's an example here. What you'll do is you can choose to have it not have an action. For example, when you have error, if you have a max quit count, you may want to suppress it halfway through. Suddenly you ran it, you realize, hey, look, I hit 2 and it's going to die. You can actually change the action also from the command line. You can do this either using an additional reporting object that you have compiled into the sim, but this is an easier way of doing it, using an existing executable. For a given component, I'll give you an example here. For UVM info, you can choose this particular value that says don't take any action when you see UVM info. What this does appears a little cryptic. What it really does is there may be a count of the number of info messages that you're getting from a simulation. And you may have chosen to take some action based on that. This thing will shut it off. So there's a lot of options that are available with the command line processor. The recommendation I have is that you go look at the doc and verification becomes hard across UVM and Perl scripts. And that's pretty much it. He has a shameless plug here for a DV rules product that he puts out.